and he's going to talk on the legacy of Abel in algebraic geometry.
Thank you. It's a pleasure to be here on this 50th anniversary of IMPA to bring congratulations from the mathematics community, from the Institute for Advanced Study. And I have here, for the occasion, Jacob, if you'll come down, a little memento. It's a plaque that just says it's congratulations on the 50th anniversary.
Thank you very much.
From Excuse me?
Should appear.
Oh, you want this on camera? Okay. I didn't make an overhead of it. So.
Okay. Okay, thank you very much. That's
Good.
a great honor.
As many of you know, this is the bicentenary of the birth of Niels Heinrich Abel. And just last week, there was a meeting, scientific meeting, centering to some extent around the work of Abel and what has flowed out of that in the intervening 200 years. Also, it was a formal occasion for the announcement by the Norwegian Academy of Sciences and the Norwegian government, the king, of the Abel Prize. So I thought it might be appropriate here to talk a bit about Abel and specifically his legacy in algebraic geometry. He has legacies in other areas of mathematics, infinite series, integral equations, and so on. But I think it's safe to say that the main body of the work in his short life, he died when he was 26, was in algebraic geometry. And so what I'd like to do today is to review really what Abel did and what we see flowing out of that in modern mathematics. So we're having a little trouble with the spacing, but these are the topics that I'd like to go over. The first is the origins of Abel's theorem to really set the context for when he did his work in the 1820s. And then to state what Abel's theorem is, and in fact give one of his proofs, which is just a few lines. And then talk about some of the converses to Abel's theorem, which involve a lot of what we now call the modern understanding of the geometry of algebraic curves. And then talk a bit about some of the legacies in present-day mathematics. One is in algebraic geometry, and we'll have an arithmetic flavor. The second is the subject of webs. It's a very beautiful special subject in local differential geometry where Abel's theorem unexpectedly comes into play and leads to some interesting, easily stated problems. And finally, a reprise. For the origins of Abel's theorem, the classical mathematicians, meaning mathematicians of the 18th and early 19th century, were very much concerned with integrals of algebraic functions. An algebraic function is a function y of x, not single-valued, but which satisfies a polynomial equation between x and y of x. The fact that it's not single-valued didn't cause trouble classically. They chose some branch of an algebraic function. It's like choosing a square root or something and just worked locally. And I've written down what were at that time, the algebraic integrals that were of greatest interest, the hyperelliptic integrals, where the algebraic function is really a square root of a polynomial. In addition to being of interest in their own right in the development of calculus, these algebraic integrals arose in geometry and mechanics in many places. They were understood when n was 1 and 2. in elementary calculus, you learn how to resolve such an integral in terms of elementary functions when you have a square root of a linear polynomial or a quadratic polynomial. There were fragments dating primarily to Euler when n is 3 and 4. Those are so-called elliptic integrals. And in some form, the addition theorem for elliptic integrals in special cases was known to Euler and also to Legendre. In geometry, the most elementary way they arise is in the arc length on a circle, and more interestingly, on an ellipse, if you try to write the points on an ellipse parametrically as functions of arc length, then you run into this integral, just the integral of the arc length element on an ellipse, and with change of variables, it goes into the form of a hyperelliptic integral. In mechanics, just Newton's equations, and it should be a different p here. P is a polynomial. If you write down conservation of energy and resolve that equation, then you get an algebraic integral, again of hyperelliptic type. So these integrals of algebraic functions were of great interest to mathematicians of the time. They tend to view them very individually. You took a particular integral and you tried to compute it, or you tried to make a change of variables, or you looked at it in very specific ways. Abel, when he came along, completely revolutionized the way that one studies these in a way that I'll try to explain. There are two main ideas in his work. One is the notion of what we now call abelian sums, and the second is instead of trying to evaluate the integral like you would do in calculus, you invert it. That you consider the integral as your variable and the limit of integration as your unknown function, and you study the properties of that upper limit of integration as a function of the value of the integral. Those two concepts led to a very general notion of functional equations, which really permeate algebraic geometry and other branches of mathematics. Abelian equations, for example, abelian extensions, were arrived at by this method of functional equations. To explain then abelian sums, what Abel did was take an algebraic curve in the plane and take an auxiliary curve depending on a rational parameter. Here I've taken the fixed curve to be an elliptic curve. That's the solid line. That's the usual picture of a real cubic curve in Weierstrass form. And the variable curve here I've taken to be a family of conics, actually of ellipses in this case. And these two algebraic curves will meet in a certain number of points, which I've labeled just the x-coordinates, xi of t. Abel's idea was that instead of considering just an individual integral, you consider this abelian sum. That is, you consider the sum of the integrals from a fixed point to all of the variable points of intersection, okay, which depend on t. So that's this u of t. In fact, you can take any rational function of x and y, plug in y of x as your algebraic function, and you get another algebraic function of x. So it's more general than just y of x. In modern terms, what you would be doing is on this algebraic curve, the solid line, you would take the rational differential r of xy dx, restrict it to the curve, and take the sum of the integrals to these variable points of intersection. Abel's discovery was that even though these individual integrals are highly transcendental functions, and I'll say more about those in the reprise at the end, that the sum is an elementary function. So more specifically, this abelian sum is a rational function plus a sum of logs. And Abel's proof, which was very typical of his work, is it's very direct. and it's also computational. What he did was to write the integral as, and now I've written it in slightly different form, as a polynomial q, or a rational function q of xy dx, divided by f sub y as the partial derivative. The notation just makes the calculation come out better. And take its derivative, just the fundamental theorem of calculus. If you differentiate at each of the points of intersection, you get that expression for in the sums here. Now you eliminate at one of the points of intersection. I've just called it x of t, y of t. So you eliminate between those two equations, solving for x prime of t. And here you come into a denominator which involves the Jacobian. So you need some assumption that these curves meet properly. It's a technical issue. The conclusion then is that the derivative is the sum of a rational function of x and y evaluated on these variable points of intersection, sum over all the points of intersection. If you think about it for a moment, as a function of t, it's single-valued because you've summed over all of them, and it's meromorphic in the language of complex analysis because there's no way an essential singularity can arise. So a meromorphic function of t is a rational function, elementary fact, and when you integrate that, you get Abel's theorem. He gave several proofs of this. This was one. Other proofs that he gave explicit formulas for the right-hand side in special cases. And those led to rather general addition theorems, as I'll explain now. A particular class of so-called abelian integrals, that's the integral of r of xy dx on an algebraic curve, that he singled out, or what are now called integrals of the first kind. That's where the right-hand side on Abel's theorem is a constant. Or if you like, it's where this abelian sum never develops a singularity. It always remains finite. In modern language, those are the differentials that on the algebraic curve are everywhere regular. So for example, if the degree of the polynomial q, on the previous slide where I wrote it as q dx over f sub y, if that has degree less or equal n minus 3, this is of the first kind. The first instance of Abel's theorem, or illustration really, would be taking the circle and taking a family of lines, and you go through the calculation in Abel's theorem. Abel's theorem for the case where the residual curves are straight lines came out to be very explicit, the right-hand side using Lagrange interpolation formula, and this is what comes out. It's an elementary manipulation. And that's a familiar formula. If you do inversion, so what I said earlier, you take the value of the integral as your variable u, the upper limit as your unknown function phi. Of course, we know what the function is in this case. Then you get an addition theorem, which is the usual addition theorem for the sine. Nothing new there, but it illustrates the principle which applies in great generality. The next case was new. You take the cubic, and again, you take as your family of auxiliary curves depending on rational parameters, the family of lines in the plane. And that, looking at that, using Abel's theorem in that context was really what opened up what we now call the theory of elliptic functions. So you take the cubic equation, the Weierstrass cubic, as your differential. I've written it as 2 dx over f sub y, which is just dx over y, which is in classical language dx over the square root of a cubic polynomial. That's of the first kind because the degree of the numerator here is less than or equal to n minus 3. It's constant. So the integral, we'll call it u. If you differentiate this equation with respect to u, you find that the upper limits of integration, x and y, are related by y is the derivative of x with respect to u. Abel's theorem gives us the sum of the residual values of this integral at the 3 points of intersection with a line add up to 0. That's as if you choose an appropriate base point to do your integration from. And as I'll explain now, this is the addition theorem for the Weierstrass p function. In complex variable language, you would take the x-plane and you would draw cuts in the x-plane between first the two real roots of your cubic polynomial, and then the third real root and the point at infinity. Then you can choose a value for the square root, which is single valued in the cut plane. But as in the theory of Riemann surfaces, you think of this as having two sheets corresponding to the two values of the square root. If you traverse the cut, you go from the bottom sheet to the top, so to speak. So this closed curve here is one of the two closed curves on this torus, which is the topological model it's a topological model of the corresponding Riemann surface. And if you call the periods the integrals of this differential around those two closed curves, then the upper limits here, which I'll now call the p function, that's really x of u in this elliptic integral, is periodic, because if you go around a closed curve, you come back to where you start. That simply expresses the periodicity of the upper limits, x and y, as functions of the variable taken to be the integral itself. So in this way, one has constructed a pair of functions, entire functions in the complex plane, which satisfy double periodicity, and that, in fact, gives the elliptic curve parametrically as the plane modulo a lattice. I should say a word about how do you know that these functions, x of u and y of u, are entire functions of u. Actually, I'll explain that in a minute, because that's an important point. Two of the consequences of Abel's work the first was the first definition of the genus of an algebraic curve, the genus being the dimension of the space of differentials of the first kind. In modern algebraic geometry, it's called the arithmetic genus, but for a non-singular curve, it's just the usual topological genus. And that was Abel's definition, and then he computed the genus in many examples, including for a general hyperelliptic curve. It's the first computation of the genus. The second is of more special interest in the field of algebraic geometry. It's the definition of the trace, or what in algebraic geometry, this trace is a special case of what is called a correspondence. In modern terminology, you consider the simultaneous solutions of this pair of equations as a subvariety, algebraic subvariety, in the projective line with parameter t and the algebraic curve given by f equals 0. You have two projections, first onto the curve, just taking the xy coordinate, onto P1, taking the parameter t. And the trace mapping is it's the abelian sum, the differential of that as a differential, thinking of it as a function of t. Or in modern algebrogeometric language, you pull the differential omega back to this so-called incidence correspondence, and then you take the direct image. That's the trace map. This was the first case of, as I say, this together with the theorem of Poncelet about polygons that are circumscribed about one ellipse and inscribed in another, was the first illustration of the use of correspondences in algebraic geometry. A correspondence being essentially a subvariety of a product. So it's a way of sending one point to many points going one way, or one point here to many points there going the other way. One of the central notions in modern algebraic geometry, which I'll say again a bit more about later. There are two converses to Abel's theorem that I think are of interest. The first dates back to, again, 19th century, essentially to Jacobi and to Riemann. And I want to emphasize that these converses, even though in algebraic geometry, for example, they're frequently presented very globally, they're actually local. It deals with the local integration of differential equations having special properties. So here what one does is take a fixed algebraic curve, f, and you take a set of points, pi, depending on t, where t varies in some disk. So those points trace out little arcs, if we think of the one-dimensional picture, on the curve. And what you suppose is that Abel's theorem is satisfied locally in t. So that says that for each differential of the first kind, if you pull back the differential under the map locally, t goes into pi of t. Think of it now as a differential when you pull it back, something times dt. If those sum to 0 for all differentials of the first kind, then Abel says that in fact there exists a global algebraic curve depending rationally on a parameter t that cuts it out. So it's the converse to Abel's theorem. Here the genus of the curve f has to be at least 2. For genus 0 and 1, there are special statements in those cases. So here we have genus 2 or more. You can actually put this in infinitesimal form, that you have points and tangent vectors at each point. And if Abel's theorem is satisfied in the infinitesimal sense, that is, you sum up for each differential of the first kind the value of the differential at the point contracted against the tangent vector, if that sums to 0 for all differentials of the first kind, then you get this global picture. So I think of that as Abel's differential equations.
Can
Yes.
you move up a little bit?
Sorry. Yeah, sorry. The punchline was on the bottom. So what Abel's differential equations tell you is the necessary and sufficient condition that a configuration of points on an algebraic curve move rationally. And in fact, more, it tells you that if you have a configuration of points with tangent vectors at each, it gives you the necessary and sufficient condition that that be tangent to a rational motion of those points, meaning there exists a one-parameter family of algebraic curves with a rational parameter t that cuts out the initial data. The next converse to Abel's theorem is the sort of opposite type of statement. And it's interesting that this converse dates to Abel's countryman Sophus Lee. It's in Sophus Lee in the late 19th century that one first finds statements of this kind. So here, instead of the fixed algebraic curve, f, and points moving on little arcs, here we have a fixed global auxiliary, not a fixed, we have a global auxiliary curves, namely straight lines, and you have little arcs. So you have L, which is a straight line, and I'm thinking of L as varying in a neighborhood of the family of straight lines. And you have a set of local analytic arcs. And on each of these analytic arcs, you have a differential, non-zero, for which Abel's relation is satisfied. Then the theorem is that actually these little analytic arcs are part of a global algebraic curve, and this differential, these differentials on the arcs are cut out by global differential of the first kind. The flavor of both of these converses to Abel's theorem, in fact, it's the flavor of the addition theorem for the sine and for the Weierstrass P function, is that if you have some analytic data given to you in a small neighborhood, and if it satisfies a functional equation, here I've just written down for the sine and P function, functional equation, R is some rational function of two variables. If it satisfies a functional equation in a disk of radius 1, then you can define it in a disk of radius 2 by that functional equation. So sort of local analytic data propagate by means of functional equation to give you something global. That's really I think the essence of the flavor of the way Abel, of the integration of Abel's differential equations. Now I want to say a few words about the modern version of Abel's theorem, and this leads into some of the deeper questions in algebraic geometry, contemporary algebraic geometry, things that are not known. The interesting fact, I think, the new fact, is that Abel's differential equations, once you get above the situation of algebraic curves, have an arithmetic aspect to them. So I'd simply state Abel's differential equations in a special case, and on the next overhead we'll give an outstanding problem about that. So it's very concrete. You take an algebraic surface in projective 3 space defined by a polynomial equation, but here you require the polynomial equation have rational coefficients. And you ask the following question. If you have a configuration of points and tangent vectors, when is that the tangent to a rational motion of these points, where rational motion means that these points move with a rational parameter? Okay? So you're asking really for the differential equations that define rational motion of configurations of points on the surface. And the conjectured answer is as follows. I'll write it in coordinates. You imagine that your surface at each of these points projects locally one-to-one to the xy plane. So you picture some surface spread out in 3 space, and you're looking in neighborhoods of points where x and y are local coordinates. So your tangent vector looks like, point looks like this, tangent vector looks like this. You take the analog of a differential of the first kind for algebraic curves. Here it's a differential form of degree 2, and the polynomial in the numerator should be of degree less than or equal to n minus 4. These are the regular differentials on the algebraic surface. And you have a tangent vector, a differential form of degree 2, and when you evaluate a tangent vector, a differential form, you need usually a multi-vector. So if you have a 2 form, you need a pair of vectors. Here you have only 1 vector. But you can evaluate the differential form on the tangent vector by this expression here, where this object, the absolute differential of C over Q, these are the Kähler differentials of C over Q, enters the picture. So if you have any ring and a subring, you can talk about the differentials of the big ring over the small ring just by imposing Leibniz rule and killing the subring as being constants. So the absolute differentials, the differentials of C over Q, is what you get when you take complex numbers and the rational numbers. It's a strange space at first sight. Additively, it's isomorphic to the complex numbers modulo the algebraic numbers as just an additive group, C modulo Q bar. So it's infinite dimensional, highly arithmetic object. And this is what turns out from geometry to be what arises when you look at Abel's theorem for configurations of points on the surface. This has geometric meaning, and I'll explain very briefly what that is. That if you have any configuration of points, I've written it here as a 0 cycle, so integer coefficients times points, then your original algebraic surface is defined over Q. Each of these points will have coordinates defined over some field, which may not be Q, usually isn't. But the coordinates of those points taken collectively generate a field that's finitely generated over Q. Any field that's finitely generated over Q is gotten by a certain algebraic extension of a purely transcendental extension. So it looks like that. And this is then isomorphic to the field of functions on some algebraic variety defined over Q. Okay. This allows you to take these points pi, and what I'm going to use as the language is the parameters in the field. What I mean by that is you do this geometric construction And for each point in this variety S, for which this is the function field, you'll get a point on the original algebraic surface, if you think about it. It's using the fact that things are defined over Q. So it allows you to spread out this configuration of points where the spread parameters are the parameters of the field of definition of the points. So given your original zero cycle, then you can spread it out and you get a family of zero cycles parameterized by, if you like, the field. What that means is the field is itself the function field of some variety, and you take those as the parameters, that variety. So backing up just a second, if you have an algebraic curve and configurations of points on an algebraic curve, the first invariant of the divisor is its degree. So here that would just be the sum of these coefficients. That's the integral of a generator for the zeroth cohomology of, that should be the zero forms there, not one forms. If that's zero, then this configuration of points has degree zero as the boundary of a one chain, and you can integrate the one forms over that one chain. This in Riemann surface language is what is in Abel's theorem. So this is the classical case. When you come to an algebraic surface, the first two steps are the same. You have a configuration of points with multiplicities. They first have a degree. You integrate the constant function 1 over that zero cycle to get the degree. If that's zero, this configuration of points with multiplicities is a boundary of a one chain. You integrate holomorphic one forms over that. Nothing new happens. For an algebraic surface, though, the two forms are the most important algebrogeometric invariant. And you've got to somehow, starting with your configuration of points, produce something of dimension 2 to integrate the two forms over it. And the way you do that is you spread out the zero cycle. For each point S in the spread space, you write it as the boundary of a one chain. And now if you take a one cycle in the spread space, this auxiliary space S, and as you travel around that one cycle, you carry with it these one chains whose boundary is Z. That gives you something of dimension 2. So this is how you start with something zero-dimensional. First, get something one-dimensional, writing it as a boundary of a one chain. If both of those are zero, you get something two-dimensional, but it involves using the parameters of the field of definition. That's the geometric meaning of Abel's theorem. I've given the infinitesimal version of it on the previous overhead. So the conjecture, it's one of the central conjectures in modern algebraic geometry, is that Abel's differential equations, as I wrote them down as were on the previous overhead, the integrals are either rational motion or, in an arithmetically exceptional case, motion on an algebraic curve defined over Q. This is what's known, it's a variant of what's known as the conjecture of Bloch and Beilinson in algebraic geometry, for those of you who study arithmetic algebraic geometry. Now I want to turn to quite a different legacy, if you like, of Abel's work, dealing with the subject of webs. A web is a set of foliations in Euclidean space, or a neighborhood in Euclidean space, in general position. So I've drawn at the top here a three web in the plane. Through each point you have, in this case, three arcs. And the central problem in the theory of webs is to find the local invariance under diffeomorphism of a web, or more specifically to find conditions, for example, under which a web can be linearized, under which there's a C-infinity change of coordinates that makes each of the leaves of the foliation linear spaces. So, for example, for a two-web in the plane where you have, through each point, two curves, curvilinear arcs, then since you are in general position, it's clear you can straighten those out and make them straight lines. So the first interesting case is a three-web. In general, a web is called linear if the leaves of the foliation are linear subspaces. So an example of a linear web is this, that you take an algebraic curve in the plane, drawn here with a dotted line. You take a point in the plane, and you draw the tangents from that point to the algebraic curve. It's standard classical algebraic geometry that the number of tangents through each point, external point, is the same. It's called the degree of the dual. So that gives through each point, as this point varies, a set of lines, the number of which is equal to the degree of the dual. The projective dual of this construction, the space of the web is the dual projective space. So the points of the dual projective space are lines in the projective plane. So here's a point in the dual projective space corresponding to a line there. The lines in the dual projective space are pencils of lines to a point. So the lines in the dual projective space correspond to points in the original projective plane. Now if you take an algebraic curve drawn here with a dotted line, that gives you a linear web. It's really a projective duality of this construction in the dual projective plane. So the point is that algebrogeometric construction, an algebraic curve in the plane, and looking at the points of intersection with lines gives you a linear web. Another way to generate webs is to take just an ordinary differential equation, which is a polynomial in the derivative. This gives a web. The basic definition in the study of webs, which goes back to Blaschke, the theory of webs originated in the 1930s in Hamburg, Germany, with 20s and 30s with Blaschke and his students, is that of an abelian relation. An abelian relation is given by a set fi of functions of one variable such that this differential relation is satisfied. The web is given by fi equals constant, the capital fi equals constant. The abelian relation is given by functions gi of one variable such that this differential relation is identically satisfied. Where this definition comes from is on the previous overhead, taking the algebraic curve meeting lines, taking that web and taking Abel's theorem in differential form. It gives you an abelian relation. So the motivation for an abelian relation on a general web came by writing down the local version, if you like, of Abel's theorem in the case where the web comes from algebraic geometry in the second example on the previous overhead. In fact, it's a theorem that if you define the rank of the web to be the dimension of the space of abelian relations, then the rank of any web in the plane is less than or equal to this number. That number is the genus of an algebraic curve of degree n in the plane. So even though you started with a web that had nothing to do with algebraic geometry, its rank, the dimension of the space of abelian equations, is less than or equal to the genus of an algebraic curve of degree n. And the second converse to Abel's theorem that I gave before would tell you that if you have a linear web with positive rank, it's algebraic. See, that had to do with a straight line moving, meeting arcs, and then gave you some global algebraicity coming from an abelian relation. So the problem then that Blaschke and his co-workers posed was to determine all webs of maximum rank.
We'll have to move on.
Yeah. For n equals 3 and 4, all of the webs of maximum rank come from algebraic geometry in the same way as that example on the previous overhead. So for n equals 3, the maximum rank is 1. And I've written down here the abelian relation in integrated form. So I think the meaning is clear. It's a function phi1 that satisfies this functional equation. These are the three functions, x equals constant, y equals constant, x over... Excuse me? Yeah. Right. So this is the abelian equation in integrated form. The leaves of the web are x equals constant, y equals constant, x over y equals constant. And this is the functional equation that gives you the integrated form of the abelian relation. It's just the functional equation for log. For rank 3, I just indicated here how Blaschke proved that a 3-web of maximum rank 3 can be, is linear, that you take the rows as a basis for the abelian relations. The columns then give you a map into projective plane, think of them as homogeneous coordinates, that satisfy, that linearize the web using this remark about the second local converse to Abel's theorem. Life gets interesting at n equals 5. If you take 4 points in the plane and you take a 5th variable point, that's this point, then through that 5th variable point you can draw 4 straight lines and 1 conic, because 5 points, through 5 points in the plane, general points, there passes a unique conic. So this gives you a 5-web passing through that point. 4 straight lines, 1 conic. And Bohl proved 2 things. First, that this was of maximum rank, and secondly, that it's not algebraic. The abelian equations, the elementary ones, come in a similar way to this, using the straight lines. The interesting one, which comes from the conic, has this as its abelian equation integrated. So this being constant would give you the leaves of one of the equations for the leaves of the web. You'll notice here the functional equation copied from the works of Abel for the dilogarithm. If you go up to 6, 7, or 8, then the webs of maximum rank are either algebraic, coming from algebraic geometry, or composed of the Bohl web you can add 2 webs. You can just take as the foliations the union of the 2 sets of foliations. So that's what composed of means. So for n equals 6, 7, or 8, you get nothing new. For n equals 9, you get a new exceptional web, which comes from the trilogarithm. And this is due as a recent result of Hanot. I think this leads to, it's not really a conjecture, it's more a question at this point. Are all webs of maximum rank of this type? And do you add 1 new exceptional web each time you get the higher logarithms, the polylogarithms? What's interesting about this is that it's not known what the minimal number of terms in the functional equation for a polylogarithm is. In fact, Hanot's theorem proves for the first time that the minimal number of terms in the functional equation for the trilogarithm is 9. That's the first time this has been proved. And it was proved because he showed that you got no exceptional webs up through 8. So if you had a shorter functional equation for the trilogarithm, it would give you an exceptional web, which doesn't exist. So there's something, I think, quite interesting going on here between arithmetic, because the polylogs are essentially arithmetic objects, and geometry, because webs are highly geometric. In fact, that leads to the final remark, the reprise. Going back to these integrals of algebraic functions, of great current interest are integrals where you take everything defined over Q. F is a polynomial defined over Q, and you take an integral between 2 limits of integration that are algebraic numbers, say rational numbers. Right? These are objects that go way back in classical mathematics. I think the main figure here in the 1930s, 1940s, 1950s was Carl Ludwig Siegel, who built on works of Gelfand and Schneider and earlier works of Lindemann and everyone who proved transcendence of E, transcendence of pi. algebraic dependence of values of the Bessel function at 3 points, things like that. So the arithmetic properties of these integrals of algebraic functions are a topic of, as I say, of great modern interest. There's a very interesting paper written recently by Zagier and Kontsevich that gives sort of an overview of this whole subject. The general feeling is that these should be transcendental. Okay? I mean, that's what one proves. They're transcendence results, or Siegel proves not only are they transcendental, but they're bounded away from being algebraic numbers in some precise sense. If you have an integral around a closed period, around a closed loop, then we'll call that a closed period. So the periods and their higher dimensional analogs, where you have multiple integrals, not just integrals of one forms, but Q forms, generate a field. It's a countable field, somewhere between the algebraic numbers and the complex numbers. And I think, well, it's not myself, many people feel that, that these are among the most beautiful and mysterious of numbers. For example, no one has ever found explicitly a number which is in C but not in pi. There's no known number that's transcendental but not a period. On the other hand, there's just a countable set of them. And all sorts of questions that one can try to ask, very elementary questions, elementary sounding questions, lead you into deep mathematics. And I think this being the final point, into algebraic geometry. There's a very general philosophy or conjecture due to Grothendieck in the 60s that the only relations over Q among closed periods, so that's the periods around cycles, right, that those arise from geometry. And let me explain what that means. The most common relation among closed periods is what's called the first Riemann bilinear relation. So that's a quadratic relation on the periods of the differentials of the first kind on an algebraic curve. And algebra geometrically, it corresponds to the diagonal in the product of the curve with itself, viewed as a correspondence. Grothendieck's general conjecture would be that all of the polynomial relations over Q among closed periods come from correspondences. A very beautiful problem. More generally, one can look at algebraic relations over Q among periods in general, not just closed periods. And Abel's theorem, the arithmetic form of it, is the only relation, and its generalizations, is the only known relation. All right? That's some sort of extension of Grothendieck's general philosophy, if you like. Because Abel deals with something that's not just topological. That's when you go all the way around a loop. Abel deals with things that are deeper in a way. So I know of no relation, general relation, with Q coefficients among periods other than those that arise from Abel's theorem. So I close with just the thought that maybe the 21st century, the arithmetic aspect of Abel's theorem will be a major subject for the 21st century. Thank you.
Questions or remarks? Okay, so let's thank the speaker again.